seen what a vector function is, and in a way it should remind you of the parametric forms of regular equations that we saw right at the beginning of the semester. Except now, because there are three components, we have three different parameters. And what we're going to do in this particular section, once we have the derivatives and integrals, is also going to run parallel to what we did with parametric equations. That is, we learned how to find the derivative, right? The integrals. And then we did a bunch of applications, right? Like areas and surface areas and arc lengths. So that's sort of the trajectory that we are going to go here, except now we are in 3 dimension and we are thinking of these as vector functions, right? So first thing is derivative. So if we have a vector function r of t given by the three components f, g, and h, which is the same as ft I cap, gt j cap, and ht k cap, where f, g, h are differentiable functions. They do have to be differentiable so that we can find the derivative. Then the derivative r prime t is quite simply the derivatives of each of the component of the vector function, or written in the ijk form, that is that is what that would look like. Then we have a definition which says that a unit vector, remember that means a vector of length 1, that has the same direction as the tangent vector is called the unit tangent vector, as you would expect to call it. T and is given by, so that's the unit tangent vector, r prime t, which we can find by the given definition above, divided by the magnitude. So this is a general thing that we have seen, right? Anytime you want to find any sort of unit vector, you take the vector and you divide it by its magnitude. Let's look at an example. Find the derivative of the vector function given by 1 plus t cubed in the I cap direction, t times e raised to negative t in the j cap direction, and sine 2t k cap. So the solution is straightforward as long as you remember how to find the derivatives of each of these. So 1 plus 3t cubed using the polynomial rule is 3t square I cap. For the second one, you have to use product rule. So derivative of t, which is 1, times e raised to negative t, plus t, derivative of e raised to negative t, which is e raised to negative t times negative 1, j cap. And chain rule here, derivative of sine is cosine, and derivative of 2t is 2. So clearing out things, 3t squared I cap plus e raised to negative t 1 minus t j cap plus 2 cosine 2t k cap. Now there can be a second part of this question which says find the unit tangent vector, but where? At t equals 0. So all you need to do is I need to find this exact vector. So that's a 0 I cap plus 1 j cap plus 2k cap. So this is j plus 2k, or 0, 1, 2. So the tangent vector at 0 is going to be this derivative divided by the magnitude. So 0, 1, 2 divided by square root of 0 squared plus 1 squared plus 2 squared, which means it is 0, 1 over root 5, and 2 over root 5, or in the JK notation, this is 1 over root 5 j cap plus 2 over root 5 k cap. Okay, let's look at another example of how this derivative, remember, means also tangent, right? So wherever there's derivative, whenever we're talking about derivatives, we're talking about changes, we're talking about tangents. So you can have a problem which says something like find the parametric equations for the tangent line to the helix with x equals 2 cosine t, y equals sine t, and z equals t at the point 0, 1, pi over 2. So since we're trying to find the equation of a tangent line, it means we have our vector equation 2 cosine t, sine t, t, and we can find the derivative, which will be negative 2 sine t cosine t and 1. So what is the tangent vector at this point? 0, 1, pi over 2. Now here we need to do a little bit of work, because what we are given is actually that x equals 0, right? So we're given 2 cosine t equals 0, sine t equals 1, and t equals pi over 2. So t is pi over 2. So what happens at pi over 2 when you plug this in? Negative sine pi over 2, cosine pi over 2, and a 1. Sine pi over 2 is 1, so this is negative 2, 0, 1. Now, so what do we know about the tangent line? The tangent goes through which point? It goes through the point where we're finding the tangent, right? So it goes through the point 0, 1, pi over 2. And what's its direction? And is parallel to, that's what direction means, the vector negative 2, 0, 1. How do we find the equation of a line given a point and its direction? Well, we can do that by using x equals 0 plus negative 2 times t, y equals 1 plus 0 times t, and z equals pi over 2 plus 1 times t. So you get the equation, the parametric equation of the tangent line is x equals negative 2t, y equals 1, and z equals pi over 2. And this is from the previous section. Recall, you have a point x naught, y naught, z naught, and you have some direction, right? given by a1, a2, a3, then the equation of the line in parametric form is x naught plus a1 times t, y naught plus a2 times t, and z naught plus a3 times t. Okay, that's what we're using here to find the equation of the tangent line. Okay, now let's look at some of the differentiation rules. Some of them are pretty straightforward and similar to the ones that you've seen in one dimension. And some of them are not going to be the same. So we'll elaborate on those. What if, well, the addition as in one dimension is simply the addition of the derivative vectors. So nothing strange happens over there. Next, if you have a constant multiplication, once again, nothing new with the constant multiplication, then you can just pull the constant outside. The next one is, now there are three different or four different multiplications that we can work with here. You can also have a functional multiplication, right? Ft, where f is no longer a vector valued function, it's just a regular old function of t. In this case, we have a product rule scenario. So what we do here is take the derivative of the function ut plus ft, which is not a vector function, derivative of u prime t. In the next multiplication, now you can have two vector valued function and they are combined using the dot product. So once again, this will be similar to your product rule, where you take the derivatives one at a time. Then you have another multiplication. Because u and v are vectors, you can also talk about their cross product. And once again, in this case, we will have a product rule kind of scenario where you're going to take the derivatives one at a time. But keeping in mind here that the order hasn't changed. It's uv and not vu, because in a cross product, that would be something different. And the very last one is if I have a u of f of t, meaning this is a chain rule scenario. I think I put an extra one here. Oh no, I did need that. Chain rule, so it will be f prime of t times u prime of ft. So this is pretty much the same as the chain rule scenario that we have. Okay, last result here is a theorem. And the theorem basically says that if the magnitude of a vector valued function is c, that is a constant, then r prime t, which is a derivative, is orthogonal to the vector valued function for all t. Okay, and this can be proved quite simply as take this RT, dot it with itself. When you dot product a vector with itself, what do you get? You get the square of the magnitude. Now, if the magnitude is a constant c, then the square is also a constant c. This is also a constant. Now, if we take the derivatives on both sides, Derivative of c squared is 0. Derivative of this dot product will follow the product rule. So take derivative of this dot r plus, keep the first one as it is, take the derivative of the second. But this becomes 2 r dot is 0, or that this dot product is 0, and this automatically implies that these two vectors are orthogonal, because we've seen in the unit for dot products that dot products coming out to 0 means that the vectors are orthogonal. So we're going to end this here, and the second part will be about integrals.